I'm going to explain that integration rule that Feynman was using. This is also known as Leibniz Rule in calculus. This is a pretty advanced method of integration that is not commonly taught, and it is used to tackle integrals that can generally not be solved using standard approaches such as U substitutions or integration by parts or combinations with the chain rule or standard integration, etc. The Leibniz rule says that if we have an integral of a function of two parameters between two boundaries f of x and t, we can bring the differentiation sign inside the integral. Notice that this is only true if the points a and b are actually constants in terms of the other parameter. So the derivative with respect to x is actually equal to a partial derivative with respect to the variable x in the x world in this integral. Now let's apply this rule to an integral which cannot be solved using standard methods. We need a different tool, as Feynman would have said, namely the integral between 0 and infinity of sine of x over x dx. One of the first things that we're going to try and do would be to try and get rid of this x in the denominator of this function. So let's just introduce another function. Let's call that, I don't know, let's call that j, which will be of two parameters. We're going to introduce a new parameter. I'm going to stick with that notation that we have up here. So I'm going to call that new parameter t. And this function j will be a function of both x and t. So let's say that the function is actually the integral from 0 to infinity of sine of x over x, and that will be then multiplied by e to the minus tx and then dx. One of the things that we're going to do now is we're going to differentiate that function with respect to the new parameter t. So I'm going to just say that dj by dt is actually equal to d by dt of this integral. Now at this point I'm going to apply Leibniz rule. I'm going to be differentiating underneath the integral sign. So I'm going to turn that integral to a partial derivative, and I'm going to simply say that this integral will then be equal to the integral from 0 to infinity partial derivative with respect to t of the function sine of x over x, which of course is a constant when we're looking at the differentiation with respect to t. And then this of course is multiplied by e to the minus tx dx. Now the only thing which is of course a function of t within this function is actually e to the minus tx. So this integral over here will actually be equal to the integral from 0 to infinity, and we're going to have sine of x over x. And now let's differentiate underneath the integral sign. So the integral of minus tx will be equal to e to the minus tx multiplied by the derivative of minus tx with respect to t. Maybe I should just write this down in a different color over here on the side. I'm actually just using the chain rule. So the derivative of minus tx with respect to t, so d by dt of minus tx is of course just going to be equal to minus x. So that's what we need to multiply by. So let's just do that. So I'm going to include my minus sign here, and I'm going to add a little x right at the end. Now notice that we have now achieved our goal, so we can cancel out this x. So what we are left with is an integral which is minus the integral from 0 to infinity of sine of x e to the minus tx dx. And I've missed a little dx over here. Now this is an integral that we can actually evaluate using some standard integration techniques, namely integration by parts. So let's now apply integration by parts. Now let's do this pretty complicated integral actually, which could be a whole topic of a whole nother video, using integration by parts. Just to remind you guys, the theorem for integration by parts says that the integral of u dv is equal to the function u times v minus the integral of v times du. Now I've applied this for this integral. Now let's say that u is sine of x. This automatically means that du is equal to cos of x dx. If our function dv is e to the minus tx, then v will be e to the minus tx, well, the negative e to the minus tx divided by t. We can see that if we differentiate that, we get another factor of t, another factor of negative t, meaning that dv is e to the minus tx. So let's apply this to this integral. So the integral of sine of x e to the minus tx dx will then be equal to minus sine of x, which is our u, and multiplied by e to the minus tx. The minus sign comes from the fact that our v is e to the minus tx, so I've just brought this out here, divided by t, of course, minus the integral of minus e to the minus tx divided by t times cos of x dx. Now if we were to work this through for this next line over here, all I've done here really is converted the negative sign to a positive. So now we are in a situation where once again we have the integral of sine of x e to the minus tx dx being equal to minus sine of x e to the minus tx over t plus this new integral that we have just derived. So we must apply our rule for integration by parts yet again. Now in this case, for this integral, shall I highlight this actually? For this integral, I've applied the rule for integration by parts. If my u is cos of x, then du will be minus sine of x dx, and if my dv is e to the minus tx divided by t, then my v will then be e to the minus tx, or negative e to the minus tx divided by t squared. Okay, well, let's apply this once again. So all I've done here is just copied this line out, and now I actually get a factor of u times v. Now u is cos of x, v is e to the minus tx divided by t squared. Therefore, this factor here is actually uv, so minus cos of x e to the minus tx divided by t squared. Take away our new integral from the integration by parts, which is v du. Now our v is e to the minus tx divided by t squared. The negative sign, I've just taken that outside of the integral, multiplied by du, which is minus sine of x dx. And what I have done on this next line over here is simply rearrange this equation so that both integrals are on one side of the equation. I've taken the factor of plus 1 over t squared outside of this integral sign over here, simply because this is a constant when we are integrating with respect to dx. So we get that the integral of sine of x e to the minus tx plus 1 over t squared, this is this term over here, sine of x e to the minus tx dx, will then be equal to this expression left over here. Now if I take a factor of minus 1 over t squared, I get a factor of t multiplying the sine of x e to the minus tx plus cos of x e to the minus tx. Now what I will do then is try and essentially multiply both sides by t squared. So if I do that and then factorize the left hand side out, I am going to get t squared. Well, actually, let's not hurry up too much with the steps. Let's include as much detail as we possibly can. So yeah, let's do that. We're going to get t squared, the integral of sine of x e to the minus tx dx plus the t squared over t squared. So t squared over t squared, which is going to get cancelled out, of course, times the integral of sine of x e to the minus tx dx. That will then be equal to minus 1 over t squared t sine of x e to the minus tx plus cosine of x e to the minus tx. We're almost there, and one thing that we need to do as well is multiply the right hand side by t squared as well, which will also get cancelled out. The negative sign though will remain. Okay, well, let's factorize t squared out, or let's factorize the integral sign. So I'm going to say that the integral of sine of x e to the minus tx dx, and then we're going to open some brackets, and we're going to have t squared plus 1 will be equal to minus, and over here we could actually factorize e to the minus tx out. What we're left with is t sine of x plus cosine of x, like so, and we're nearly done. We finally are going to get that the integral of sine of x e to the minus tx dx is equal to minus e to the minus tx t sine of x plus cosine of x divided by t squared plus 1. Excellent stuff. This was quite a long example of integration by parts. It's been applied twice. Remember, our job was to evaluate this integral sine of x e to the minus tx dx. Now let's go back to our integral that we differentiated originally underneath the integral sign. Okay, well, let's go back to this definite integral. Now that we know that the integral of sine of x e to the minus tx dx is equal to this expression over here, notice that I've done a couple of things. First off, we had some minus signs initially, and what I've simply done is I've turned them into plus signs because the two negative signs are essentially going to cancel out, giving us positives. Well, we need to evaluate this expression at 2 points. So we must really think about what the limit of these functions will be as essentially x starts to approach infinity. Well, the dominating term in this expression is the exponential, which changes far more rapidly compared to sine of x, cosine of x, or t squared. Essentially, as long as there is a factorial, whatever happens to the exponential will dominate this expression. Because this is a negative exponential, essentially this is the mathematics of exponential decay. So as x is approaching infinity, e to the minus tx, assuming that t is a constant, is a parameter which is a constant, will slowly start tending towards 0. So the first term, which is that function at infinity, will be 0. From that, we need to take away our function evaluated at 0, which is our second boundary or our first boundary for the definite integral. Well, this will be equal to minus e to the minus 0, or let's just say 0, of course, multiplied by t times sine of 0, which is 0, so this whole term will actually be 0, plus cosine of 0, which is just 1. So that will be like that, and there's no x underneath, so we're just going to essentially write down t squared plus 1 over here, so t squared plus 1. Now this will then of course be equal to e to the 0 is 1, so this will just be minus 1 over t squared plus 1. We are definitely approaching the end of this very tricky integral. However, in order to proceed, we need to remember what we did at the very beginning when we were differentiating underneath the integral sign. So remember, this is actually dj by dt that I've written down over here. This is when we actually differentiated underneath the integral sign. So we need to integrate back again to actually get the function j. Well, let's do this. So what we're going to do is take this expression and we're going to integrate that with respect to t. So the integral of minus 1 over t squared plus 1 dt, this will actually give us our function j, will then of course be equal to negative inverse tan of the function t, and because this is no longer a definite integral when we are integrating with respect to t, I'm going to add in a constant of integration. Now this function j was actually the new function that we kind of invented in order to cancel out this x over here. So we can set this expression here to essentially just the integral from 0 to infinity of sine of x over x. So let's just write this carefully, sine of x over x e to the minus tx dx. So in order to evaluate this integral, we should really be choosing a constant value for t. So what I'm going to do is I'm going to evaluate this expression j. So I'm going to take the limit of j essentially as t approaches infinity, and it should become apparent why I've chosen infinity and not a different value. Now the limit of inverse tan is actually a standard limit. It is pi over 2, so this will give us minus pi over 2 plus a constant. And now look at the right hand side of this equation. Once again, the dominating term is e to the minus tx. So this, as x is increasing towards infinity, this whole function is essentially tending towards 0. And if this part is tending towards 0, then once we integrate that, it will be the dominating part of this integral, and this whole right hand side will be tending towards 0. So this integral is now turning into a pretty simple function. Finally, in fact, we can simply say that our constant is equal to pi over 2. So now that we have our value for this constant, we could go back into our original function j and actually calculate our sine of x over x integral by setting the value of t to be equal to 0. So let me just write down our original expression for j, and I'm going to say that j is equal to the integral from 0 to infinity of sine of x over x multiplied by e to the minus tx dx. We now have an expression that we have derived this. We know that this is equal to minus inverse tan of t plus a constant c, which is of course equal to pi over 2. And our final step would be to set our new parameter t to be equal to 0. Why do we set the t to be 0? Because then this part here, e to the minus tx, will then be equal to 1, because e to the power of 0 is, of course, well, equal to 1. Okay, so looking at that, we are going to get that when t, should we just write that when t is equal to 0, the integral from 0 to infinity of sine of x over x times by 1, which is the e to the minus tx part, which I'm not going to write, dx will be equal to minus inverse tan of 0 plus pi over 2. Well, hang on a minute. Tan of minus, or inverse tan of 0 is just 0, so we finally have an answer that the integral from 0 to infinity of sine of x over x dx is equal to pi over 2. This is an incredibly elegant result that we've derived by doing a lot of calculus. Well done for following all the pretty interesting and complicated mathematics through this video. Thank you very much for watching, and I will see you in the next video.